we must introduce some further notation since we have defined the matrices. So first of all, a matrix is bounded by two braces, a left one and a right one, in order not to create confusion about where one matrix ends and the next one begins when we write them one next to the other. Therefore, they will be written like this rather. Okay, so this is one, this is the second one, and this is the third, and this is the fourth. Okay, so usually we will denote matrices with the capital letter, for example A, and so we have two options to write a matrix A. One is to write explicitly its coefficients, so we open a big left brace, and then the first one will be a scalar which we call A, but this A will have to depend on two indices. Being this the first one, meaning the first one in the first column and the first row, it will be placed in the place 1 1 as explained in the previous lecture. And in order to denote the placing of this real number, we will use two indices subscript here on the letter A. Okay, so this will be the coefficient A11 placed in this point of the matrix. Now, as we move right bound on the first row, as we explained, the next coefficient will have the second index up by 1. Therefore, the coefficient will be denoted as 1, 2, and so on, until we go to the last one, let's say A1K. Okay. Now the second row. So if we move southbound from A11, then we will have A. Now the placing, as we introduced the convention before, we'll have the first coefficient, the first index moving up by 1 this time, so it will be 2, 1. Then as we move right bound, we'll have the second coefficient in position 2, 2, and so on until the last one will be A 2, K. So this matrix will have K columns, so on until the last row will be A. Let's say the first index will be some H, but the second index will be 1, just like all those at the same column, and then A H, 2, and so on until A H, K. Now this notation has the advantage that you have all the placing of the real numbers of the matrix, but it takes a really long time to write any matrix like this when it is not necessary, especially when it is not necessary to express every single coefficient of the matrix. So there is a more compact way that introduces the notation of the coefficients of A inside the matrix without expressing all of them in the sketchbook. It is this one. So this is exactly the same as writing. I open a parenthesis, a smaller one, and then I will write just A I, J. Now I will have probably to express if it is necessary. If it's not necessary, this will be enough to describe A. With the we have the advantage of knowing that when we will meet in the notation, in the writing, coefficient A depending on two indices, we know that that will be a coefficient of the matrix big A. So if you want to specify the number of rows and columns, then we'll have to add some subscript here to the parentheses, so we might write, for example, something like A going from 1 through H, and J going from 1 through K. Okay, this is optional. It depends whether we want to specify the dimensions of the matrix or just introduce a notation for the coefficients of the matrix. So this is the first notation we'll have. The second notation is to introduce the set of all matrices of a specified number of rows and columns. Okay, it is useful to introduce a compact form to denote this set, because this set will be appearing many times in these lectures. So we will denote by M, and then we open a parenthesis and we'll write the number first of rows, let's say H, and then the number of columns K. Okay, so this is consistent with this example here, A. So this is going to be the set, so we open the curly bracket, of matrices with H rows and K columns. Okay, so for example, A was an element of this set. As previously mentioned, the reason of restricting ourselves to arrangements of scalars, arrangements of real numbers in a rectangular shape, is because we want to introduce an extra algebraic structure to these objects, which is going to be different from the sum and the multiplication by scalars, which give the set MHK a structure of vector space. Okay, so we already know that this is a vector space by what we have said the previous lecture, so we know that this is a vector space. Now, some of the matrices can actually be multiplied together. So the extra structure we are talking about is a multiplication. Now, multiplication will not be an inner structure for any set, for any vector space of the kind MHK. There has to be a certain compatibility between the matrices in order to be multiplied together. Therefore, let's start with definition. So the condition in order to multiply two matrices is the following. So we pick a matrix A in MHK, then a matrix B, capital B, in MKR. Okay. Now, in this case, we can define a new matrix obtained from A and B, which we call A times B, and this matrix will belong to the set M H R. How do we define this operation? So we have to introduce, since the operation will be using the coefficients of each of these matrices, we have to introduce the notation for them. So A will be Aij, and the matrix B will be bij, we introduce notation for a times b as well. So a times b will have coefficients which we will call Cij. Now we'll have to define how to compute Cij from the a's and the b's. So then Cij will be computed from the a's and the b's by means of the following formula: is sum for s that goes from 1 to k of the product of the coefficients ais times b s j. Okay, so this is the formal definition. Let's see what this amounts to graphically. Okay, so let's assume, for example, that the matrix A is the one on the left, is, let's say, a rectangular shape of like this. Okay, so we said that A belongs to MHK, therefore there will be H rows and K columns. So we multiply this on the right by a matrix that B will belong to MKR, so there will be K rows. So let's say K rows. And okay, number of columns may or may not be greater than K. Let's say like this, I don't know. This will be R. Okay. So this product will be a matrix that dimension-wise will have the same number of rows as A, so H, and the number of columns of B, so R. Okay. Now Cij, let's say the Cij lies here. Let's say here maybe. Okay, so it will be in the ith row and jth column. So what are the coefficients in these two matrices that concur in computing Cij? So we have to take, let's see here, we have k scalars from A that are they all belong to the same row, because you see here in the sum in the sum it will be the second index that will be changing its values. The first index will be fixed I. So if we fix the first coefficient, it's like if we fix the row, the row of the scalars. Therefore, fixing the row I and moving all the columns S from 1 to K, we will be basically focusing on the ith row here, in the matrix A, and for the matrix B, on the other hand, we will have the second index fixed j, and that will just block the column. So the column will, the jth column will be somewhere here, and that will be fixed. And varying the first index means that we will be running the coefficients of the matrix B through all the coefficients of the jth column. So these will be the coefficients that will be used from the matrix B to compute the product. Okay, so coefficients from here, matrix A, and from here, matrix B. And how do we actually find the exact value of Cij? Well, we start from the first one, which is going to be in the matrix A, which is going to be A I 1, and so for s equal to 1 we will be here in the matrix A, and this coefficient will be multiplied with the first coefficient of the jth column in B. So the first coefficient here will be B 1 j. Okay, so for s equal to 1 we will multiply ai1 times b 1j. Okay, so this is the first summand. So a I1 times b 1j. Second summand will be the one obtained for s equal to 2. So we will be at the second coefficient in both vectors. So first ith row we will have the second coefficient ai2, and here we will have b 2j. And what do? We just multiply together again. So ai2 times b2j, so on, until the last coefficient will be for s equal to k, and it will be ai k times b k j, and graphically this will correspond to the last coefficient here, a I k times the last coefficient of the column B, b k j. This is the description of the product matrix of A times B.